Alright, this is your 6.5 notes, rational functions, rational equations. So what a rational function is a function of the form p of x over q of x, where p and q are both polynomials, okay, and q can't be the zero function. So just basically the stuff we've seen in the last two sections, 6.3 and 6.4, those polynomials, that's what we're dealing with as our numerator and denominator now. Alright, a vertical asymptote. A vertical asymptote occurs in a rational function if a value of x makes the denominator equal to 0, but it does not make the numerator equal to 0. Okay, so we're looking for numbers for this example down here. We're looking for numbers that'll make x plus 2 equals 0, right? But it doesn't have to make x plus 1 equals 0. It's just the stuff that makes the bottom 0. Alright, so what we're going to do to find a vertical asymptote is, the first thing we do is set denominator equal to 0. Alright, so x plus 2 equals 0. Alright, obviously, and solve. So subtracting 2 from both sides gives me x equals negative 2. Okay, now you'll be able to just do this by looking at it a lot of times. Alright, so that makes the denominator equal 0. Now, if it makes the numerator equal to 0 too, it's not an asymptote. So if I took that negative 2 and I plugged it in up top, I get negative 2 plus 1. Well, negative 2 plus 1 is negative 1. That's not 0, so that means that value of x is a vertical asymptote. Okay, so the second thing we do is determine if it makes the numerator equal to 0. If not, it is a vertical asymptote. Alright, so we checked it. It did not make the top equal to 0, so it is a vertical asymptote. Alright, and sketch the graph of this thing. So I wanted to show you something in particular about this. If I use my calculator and I put in parentheses x plus 1 close parentheses divided by, you got to put the parentheses around it, x plus 2. Alright, this is what it looks like on my calculator. This is a TI-83. Now TI-84, you guys won't see that line, but on TI-83 it does show it. But where that line is at negative 2. If you can press the trace button, you can press to the left and you can see that it has that weird funky looking line taking place right around x equal to negative 2. And if I go past it, notice now my cursor's up here. Okay, so what basically just happened is that at negative 2 we get a vertical asymptote. Now when you graph these for me, I want you to use a vertical dashed line to represent where the vertical asymptote is. Alright, so there's our vertical asymptote. Alright, and notice as I move left to right, let's press again the trace button. I'll hit 6 just to kind of move us over here. And then as I move to the right, notice it gets closer and closer and closer and closer and closer to 1, to y equals 1. And if I go like to negative 8 and go to the left, it's getting closer and closer to 1. And I'm going to extend the window just so you can see. Well, let me just go to the table, and you can see as I make my way further and further and further into the negatives, right, this thing gets closer and closer and closer to 1. Right, and as I make my way further and further in the positive direction, again, this thing gets closer and closer and closer to 1. Alright, now we'll talk about that later. That's what we call a horizontal asymptote. If it's approaching a value on the left and right side of the graph. Okay, but to help us graph this thing right now, I just want to give you a free preview of that. Alright, go back to your graph. Alright, this is approaching 1 as we go to the left, and as we get to that asymptote it bends upward, so it doesn't look like this. And actually it's going to kind of hug this asymptote, and then as it gets closer and closer here, it bends upward and gets closer and closer and closer to the vertical asymptote, but it never touches it. And then on this side, let me get my trace again. 0. See what my y-intercept is, a half. And if I hit -1, remember the numerator was x plus 1, so at -1 we hit 0. So on the other side of that vertical asymptote we cross at -1, hit the y-axis at a half, and then we get closer and closer and closer to that horizontal asymptote, but we never get there. Alright, so these things are usually going to have this kind of look to them, where they break apart at a vertical asymptote. If there is a vertical asymptote, it'll look like these. Alright, use that trace button on the calculator, but remember, if you have a TI-83, this thing is actually not there, so don't draw it. Make sure you don't draw it. It's just the rest of the graph is what you're responsible to draw. Those with an 84, you know, you're not going to see that. You're going to see something that looks more like just these two black pieces here. Alright, here is a function, C of P. It models the cost to remove P% of a pollutant from some type of industrial site. So we want to graph this function on this window. Alright, so I'm going to plug this into my calculator and graph it in the window that they tell me. Remember, this is when they give you these brackets like this. This is x min and x max. And then this is y min and y max. Alright, so I've got the function put in here. Again, I replace p with x. Okay, I do need parentheses around that denominator. Anytime you have addition or subtraction in your denominator, you gotta put parentheses around there. Same with your numerator if you have addition or subtraction. So get in the habit of doing that in this section. Now I don't have addition or subtraction, I have multiplication up here, so it's okay for my numerator. It's not okay for your denominator, even if it were multiplication. So get in the habit of anything on your denominator, putting a parentheses around it. And if there's addition or subtraction in your numerator, parentheses around it as well. My window, -100 to 200. Alright, I changed my scale to 10. And then -4000 to +4000. Again, I changed my scale to 500. Alright, I hit graph. And there's what I see. And again, there's that asymptote right there. Alright, so I graphed it in that window. Does the graph of this function have a vertical asymptote in this window? Yes. Where at p equals 100. Okay, because there's where the denominator would equal 0. Alright, but you can also, I mean, if you don't get it from there, you can also get it from your trace value. There's our asymptote. If I hit trace and I start making my way towards the asymptote, where does it take place? You see this is at 81. Say we're still positive at 97. And then watch what happens when we go across. Now we're in the negative. So it takes place at 100. But the easy way to get it is just what makes your denominator 0. Alright, for what values of P does the function serve as a model for the cost of removing a pollutant? Alright, so what this is basically saying is, yeah, this thing keeps on going beyond that, but what's the implied domain because of the fact that this is a pollutant? And that's 0 less than or equal to p less than 100. Okay, because we can't remove 125% of a pollutant. All right, you hear people say, you know, he gives 110%. All right, well, that's a nice little cliche, but it doesn't apply when you're actually, you know, trying to remove a pollutant. When you're actually, you know, we can't remove 110% of a pollutant. So anything from 0% all the way up to 100% serve the purpose. So we're going to regraph this thing using, instead of negative, which doesn't make any sense, up to 200, we're going to make our x minimum 0 and our x maximum 100. Alright, and then graph it. And really, the cost doesn't need to be negative either. So I'm going to make that y minimum 0. So there's our function. Okay. Now I'm going to scroll down here. I've put a graph down here. This would be our answer to part D. To come up with this model. Alright, now what does the part of the graph near the vertical asymptote tell us about the cost of removing pollutant? So what it's asking in part E, again, here's our vertical asymptote. It's saying, what is the part of the graph near the vertical asymptote as we come across this way? Tell us about the cost of removing the pollutant. Well, notice, you know, to go from 0 to 20, the cost didn't go up that much. To go from 20 to 40, still didn't go up that much. It went a little bit more than it did from 0 to 20. From 40 to 60, it starts to get up, you know, much higher, and then from 60 to 80, it goes way high. But notice from 80 to 100, it's astronomically high. I mean, it starts bending up so fast that it's unattainable. We can't get there. So the cost to remove pollutant the cost to remove pollution becomes more and more expensive. The closer P gets to 100%. Okay, if we've already removed, you know, 95% of it, the cost to remove any more starts to become astronomical. But if we've only removed 10%, the cost to remove the next 10% is not that bad. But as we have removed so much of it, and so little remains, or such a small percentage remains, the cost to keep removing goes up, because we're out there, we're doing the same procedures, and there's so little left, it's hard to remove anymore. Alright, but that's an applied problem. Asymptotes have meaning just like an intersection has meaning. Right? Just like a x-intercept has meaning, or an intersection of two graphs has meaning. Asymptotes will have meaning in this section in the homework you're doing. Alright, a horizontal asymptote, like we talked about before, we were doing this problem at the beginning. And I told you we'd come back to horizontal asymptotes in a second. We're back to them. A horizontal asymptote occurs at the ends of the graph. The right side, which means x approaches positive infinity, or the left side, x approaches negative infinity. So what this is basically saying, back to this page, this was the line y equals 1. Okay, this was the line x equals -2. This is the horizontal asymptote, is as we move to the right end or the left end, the further to the right and left we go, the graph gets closer and closer and closer to that y value. And that means that that is an asymptote, a horizontal asymptote in this case. So that's what this is saying down here. As we go to the left or right side of the graph, if the function is approaching that particular value, what they're calling a here, then y equals a is the equation of the horizontal asymptote. Now, how do we find it? A quick, easy way is use the degrees. So this looks intimidating, but the thing that all you need to know here is n is the degree of the top. Alright, and m is the degree of the denominator. Okay, and this is saying n, which is the degree of the numerator. If the degree of the numerator is less than the degree of the denominator, then your horizontal asymptote is the x-axis. Okay, if they're equal, right, meaning that the degrees are the same, the highest powers are the same, then you divide the leading coefficients. Right, this is the leading coefficient up top, a sub n. This is the leading coefficient on the bottom, b sub m. So you divide leading coefficients. Okay, that's when they're equal. You divide the leading coefficients. And then if the degree of the numerator is higher than the degree of the denominator, then you're not going to have a horizontal asymptote. Right? So which of these methods applies? Or which of these steps? 1, 2, or 3? This is degree 1. This is degree 2. So the degree of the denominator is greater than the degree of the numerator. Or the degree of the numerator is less than the degree of the denominator. So that's 1. So that's n is less than m. So what's our horizontal asymptote? The x-axis. Alright, and you see, this is the graph of this thing. I put it into my calculator and graphed it. As I make my way to the left side or the right side, the graph gets closer and closer and closer to the x-axis. Right, it crosses it and then it starts coming back down closer and closer and closer to it. Alright, which one applies now? 2 and 2. Both degree 2. So that's 2. What do? I divide the leading coefficients. So the horizontal asymptote is y equals, the leading coefficient here is 4 divided by the leading coefficient here is 2. So y equals 2 is the horizontal asymptote. And again, there's 1, 2. So y equals 2 is where this thing is settling down. As I make my way to the right side, the graph is coming down closer and closer and closer to the line y equals 2. And again, as I make my way to the left, I'm getting closer and closer and closer to 2 for the y values. Alright, third example. X equals 3, so degree up top, n, is 3. M, the degree on the bottom, is 2, so n is greater than m. Alright, what did that mean? No horizontal asymptote. And as you see here, as I make my way to the left, it keeps getting further and further and further away. As I make my way to the right, it's getting further and further and further away. It's not settling down to a number like it did here or like it did here. Okay? So that's what that rule is saying. So again, just take the time, pause it there if you need to, but it's all about the degrees, the top and the bottom. The highest power in the numerator and denominator will determine your horizontal asymptotes. Alright, a slant asymptote. If the degree of the numerator is exactly 1 higher than the degree of the denominator, like this example, this is degree 2, this is degree 1, then the graph of the function will have a slant asymptote, meaning that the curved function here is settling down as we make our way to the left and to the right along this line. It's getting closer and closer and closer to this linear function y equals 13 plus x. Okay, that's a slant asymptote. If you look at the last example that I gave you on the previous slide, right, this is degree 3, this is degree 2, so exactly one higher, and again we had that line here, that's slant asymptote. Alright, and if you want to find the equation of this line, where this thing is settling down to, you just do polynomial long division. You take this numerator, you divide by the denominator, right, and what you end up with is a linear function, right, in this case x plus 13, plus some remainder that doesn't matter. And then observe that this rational expression, the remainder part, approaches 0 as x approaches infinity or negative infinity. So you just end up with the linear function. So using this example right here, if I take these three things and divide each by x, so 25 over x, 13x over x, well, what's 13x over x? If I split each one of these things up, 25 over x plus 13x over x plus x squared over x, what happens? Well, nothing happens here, we just get 25 over x, but here that x cancels with that x and we just get 13, and then here that x cancels with one of those x and just leaves us with 1x. That's where that's coming from. Alright, so this is the exact same as this, we just did the division. Now what this is saying, step 2 says, observe this rational expression, this right here, found from doing this division, will approach 0 as x approaches infinity. So 25 divided by x, if I take 25 and I divide by bigger and bigger numbers, like 25 divided by 100, and then 25 divided by 1,000, and then 25 divided by, just make the numbers bigger and bigger and bigger. Oops. Couple more zeros. Eventually, if I divide by a number big enough, your calculator says, alright, well that's virtually like you're dividing by 0. I'm sorry, you're dividing by such a big number that that number is virtually equal to 0. Let's see if I can actually get it to do it. Okay, well, anyway, these numbers are like negative e to negative 49. That means 48 zeros and then 2 5s. So it's virtually 0. So that piece right there is virtually 0, gone. And what are we left with? We're just left with x plus 13. So there's where that equation of that slant asymptote is coming from. Do the long division, whatever linear function's there is your slant asymptote, and just ignore anything that has the x or the variable in the denominator. Alright, now there's the big thing in this section, a rational equation. So if you want to solve a rational equation, first thing you do is come up with your LCD and multiply both sides of the equation to get rid of the fractions. Okay? And then solve your resulting equation. It's going to be some type of a polynomial once you do step 1. But here's the thing, you've got to remember to do this. This is not a good idea, this is a must. You've got to do it. Okay? I know you've had classes before where you're told to check and you really didn't have to. You have to here, okay? Because we have division by 0 potentially in the original expressions on each side, we have the potential for a solution once we change it to polynomials. We don't have to worry about division by 0, and when we solve a polynomial we get an answer plugging it back into the original, it could cause division by 0, so we have to be careful. Alright, so I'm going to do that. I'm going to multiply through this entire thing by left and right by the LCD. The LCD here is x minus 1, since that's the only denominator. And I'm going to have to distribute that through on both sides, since I have addition. Alright, so x minus 1 times x squared. And then here, x minus 1 times, this has an x minus 1 on the bottom, so they'll cancel with each other. And it just leaves me with the x up top. And over here, same thing, x minus 1 times that x. And then this x minus 1 and this x minus 1 will cancel, and we're left with plus x cubed. Alright, now this is the polynomial equation that step 2 was talking about. Solve that resulting polynomial equation. So I'm going to need to distribute again on both sides to clear out the parentheses. And I've got x cubed minus x squared plus x equals, on this side I've got an x squared minus x plus x cubed. Alright, anytime, excuse me, a polynomial equation, the only methods we've ever talked about in this course to solve them involve grouping everything to one side. So I'm going to collect everything to one side and subtract this x cubed, add an x, and subtract an x squared. So subtract an x cubed, subtract x squared, add an x. Alright, everything's gone over here. So we've got it set equal to 0. X cubed minus x cubed is 0. Negative x squared minus another x squared is negative 2x squared. And then x plus x is 2x. Alright, now first thing I'm going to do is factor. I've got a polynomial set equal to 0. I factor it. And I'm going to pull out the GCF of negative 2x. Right. Now I could have just brought out a 2x, but because this leads with a negative, I'm going to put out a negative 2x. So that leaves me here with an x, and negative 2x divided by positive 2x divided by negative 2x is minus 1 equals 0. Now set each one equal to 0. So I got negative 2x is equal to 0, or I've got x minus 1 is equal to 0. Those are the two things that are being multiplied to give me 0, so I set each piece equal to 0. Alright, this one, if it's equal to 0, then obviously x is just 0. Or, if this one were equal to 0, add 1 to both sides, we get x is equal to 1. Alright, so there's step 2 done. We solved the resulting polynomial equation, but we got to remember to do step 3. Check in the original. Alright, now what I do to check is I plug 0 in for each x here. So I get 0 squared plus 0 over 0 minus 1 equals 0 plus 0 cubed over 0 minus 1. Does that work? So plugging in, I get 0 squared plus 0 over 0 minus 1. Is that equal to 0 plus 0 cubed over 0 minus 1? Alright, 0 squared is 0. 0 divided by negative 1. 0 plus, this is 0 divided by negative 1. Alright, 0 divided by anything, as long as it's not 0, is 0. So left we get 0, right we get 0. So that one works. Now, checking the other one. The problem here is plugging in a positive 1 into that denominator for that x gives me 1 minus 1, which is 0. So that one doesn't work. For that one we divide by 0. We can't do that, so we have to throw that one out. So the only solution here is 0. Alright, so gotta make sure to check. Alright, here's a word problem example. So we want to take this gives their monthly sales in thousands of dollars, related to their advertising expenses, X, right, and it's also in thousands. Determine the amount of money that must be spent on advertising to generate 100,000 in sales. Okay, now Y is measured in thousands, so that means we're going to set it equal to just 100. So 100 is the amount of sales we want, and then 300x divided by 15 plus x is equal to that. Alright, so clear fractions again, so we're going to multiply both sides by 15 plus x. Alright, go on over here, and we get, I'm going to go ahead and distribute 1500 plus 100x equals 300x. Alright, subtract away the 100x to get your x's on one side, your constants on the other, and we get 1500 is equal to 200x. Alright, divided by 200, x is equal to, the zeros cancel, 15 divided by 2 is 7.5. Alright, and then 7.5 is x, but that's in thousands of dollars, so 7,500 is needed in advertising. For sales to be 100,000. Alright, inverse variation. So back in chapter 2 we talked about direct variation. Inverse variation, or direct variation, meant as one got bigger, the other one got bigger. As one got smaller, the other got smaller. But inverse variation means when one gets bigger, the other one gets smaller, or vice versa. So when you see something like this says y varies inversely as as x. This one says y varies inversely as the nth power of x. Okay, but notice both of them have this k multiplier. That's what we call the constant of variation. Now that's in this section because of the fact that you end up with rational expressions when you have inverse variation. Alright, so the illumination produced by light varies inversely as the square as the distance from the source of light. So if the illumination 30 feet from a light source is 60 candela, what is the illumination 20 feet from the source? So the way we do this, we declare our variables. L is our illumination in candela, and D is the distance. So this first line, the illumination produced by light varies inversely as the square of the distance. So L varies inversely means we're going to have k divided by something. What does it vary inversely as? That's what goes down here. The square of the distance. So D squared. Alright, now this is a two-parter. Well, first we need to find k, and then we need to solve for the missing variable. So step 1, find k. Alright, so we know the illumination 30 feet is 60 candela, so that's L. And then distance was 30 feet, so over 30 squared. Okay, 30 is feet, that's a distance unit. 60 is candela. Candela is a illumination unit. Alright, so K over 30 squared is 900. Alright, and then to solve for K, K equals, I multiply both of these sides by 900. So K equals 900 times 60, which equals 54,000. Alright, so there's step 1. We found K. Step 2, use that function. L equals 54,000 over D squared and solve the new equation. What is the illumination 20 feet from the source? So L equals 54,000 divided by 20 squared. Alright, and then you can just go to your calculator from there. So 54,000 divided by 20 squared, hit enter, 135. And there's our answer. Alright, so there's an applied problem using inverse variation. The hardest thing about these types of problems, these variation problems, is just understanding how to set it up. Alright, but it's going to look, it's going to have this look to it. It's going to have something equals K divided by something, and you just use the wording of the first line, or they tell you how they're related, to determine if you're going to square anything anywhere. Alright, and it's usually this two-step process. Step 1, find K, and then I didn't write it down here. Step 2 was down here. Use K to find L. Alright, or D. You know, it could have given us L again and had us find D, but anyway, it's a two-step process. Usually you need to find this constant of variation, and then after you found the constant of variation, then you can use it to solve another part of the problem.